All right. How you guys doing? You guys already started exams? Is mine the first? Two? Okay, so right a long time, right? Okay. How'd you feel about the homework?
Last question.
Okay.
I ended up using a ratio and doing it that way.
Okay. So yeah, we'll definitely talk about the last question. That one was simpler than you might think, but made you think about it outside of the box of precisely what we've learned so far. But it'll make sense when we look at it. We're basically looking at, you're given a pKa on that one. Again, we'll come over to it. And so you can see in the data where you see a difference in what's happening based on which line of that pKa you're on. And so that's kind of the point of that question. But before we get to all that, I wanted to say a couple things. One, I've not yet prepared a formula sheet, but I'm going to try to do that for you by the end of today. Certainly before so by the end of today, possibly tomorrow, or at least by Saturday. So you'll at least have a couple days to study with that. I'm going to try to have that for you today. I've not designed your exam yet either, but you can imagine that the stuff we've talked about, stuff that's on the homework, that's, we kind of know the scope of this exam, right? So you're welcome to ask me questions, but, unless you're making a suggestion with how specific you're getting, is this going to be on the exam? Maybe I'll put it on the exam, right? I just don't quite know yet, but I'm going to try to scope it to be something that parts of it might be challenging, parts of it will be, you studied that, you got it, no problem, and parts of it will be just making sure that we're all kind of on the same page. Yeah.
How are you going to be grading the homework?
Typically, I grade homeworks with some partial credit involved. First and foremost, did you put forward effort? Of course, if you get the question right and I see that you did work for it, you get full credit. If I saw you did all the pieces like you should have, but you flipped a negative sign, I'm typically pretty lenient on that kind of thing, right? So you will get partial, and that's true for the exams as well. If I'm really looking to see, did you approach it? Where were there mistakes with the approach? Homeworks, I might be a little quicker in terms of not digging as deep into the process, but usually I'm looking to kind of see those components. Did that answer your question, or? Okay. Okay. The other thing is this session that I'm recording now, I'm going to unlist it on YouTube, but I will link it within Moodle. So you'll have the permanent link for it in Moodle. But if you're just searching the YouTube channel, you won't necessarily find it there. Okay. So I'll add that to Moodle as well, along with these slides. Okay. Any other questions about the exam? Concerns? Okay, I'm going to dive into the homework then, go through this. You're welcome to kind of track, alongside what you've done already, or just kind of sit and watch. Whatever you like. If you find a question about the homework or about the exam, something you'd like me to try solving or whatever, feel free to speak up. Okay, so the first question is really tackling some of the very fundamental basics of chemistry, making sure we're all on the same page with that. And then also adding the ionic strength. Can you do those calculations? And then putting that together with the last piece of this with the Davies equation to find the activity of a given salt. Okay, so the question says, imagine we decide to do some sort of experiment with a swimming pool that is 80,000 liters of pure water, and we want to answer a couple questions here. First, what is the resulting ionic strength of the pool if we add 500 kilograms of sodium chloride? Okay, so this one's pretty straightforward. We need to know the concentration of sodium and chloride that we just added so that we can solve for the ionic strength. In fact, if we just work backwards a little bit, we could see that the equation we're going to have is going to be the amount of sodium times its charge squared. So it can be 1/2 of sodium times its charge squared plus the chloride concentration times its charge squared. That's going to be our target, right? Technically, we could think about H plus and OH minus, but those are very low concentrations typically, as we know. We'd have to have a very extreme pH for those to become kind of meaningful, and generally we just neglect H plus and OH minus for ionic strength. Okay, so those are the two things we need then. So in order to figure out how much on a molar concentration we have of sodium and chloride, well, first we can say every 1 sodium chloride will dissolve to give us 1 sodium and 1 Cl minus, 1 chloride. And the molecular weight for sodium chloride, that's what we're adding, is 58.45 grams per mole. Okay, we can then figure out, well, we added X amount to Y amount of volume. We can get that as a mass concentration and convert it to a molar concentration, or we can just get the number of moles first in the first place and then divide that by the volume and get a molar concentration. So I'm just going to say the moles will be 500 kilograms. I'm going to go ahead and convert that to grams and say 500,000 grams. And we can divide that by the molecular weight, 58.45 grams per mole. That way the grams will cancel and the mole unit will come on up to the top. This will give us 8,554.3 moles added of sodium chloride. That means there's that number of moles of sodium and that many number of moles of chloride as well. Okay, so then to get the concentration, all we really need to do, and this is not true when I'm writing it this way, sodium chloride. I'm just saying the concentration as if it stayed that way, right? For a moment, would be equal to that number divided by 80,000 liters, right? So that'll be 8554.3 divided by 80,000 liters. And that's going to be 0.107 moles per liter. Okay, so that's pretty convenient now that we have that, because we now know that that's also the same thing as our chloride concentration and our sodium concentration. Okay, then if we take a look at this formula, well, both charges are 1 or -1, so those don't go anywhere. So then we just basically have x plus x divided by 2, which is x, right? So the overall solution to this, we didn't even really need a calculator. Of course, you could put it in. But because it's such a simple system, it turns out I is exactly 0.107 moles per liter. Well, we don't really put the moles, it's kind of an equivalence, but we'll not bother with that right now. Okay, so this part pretty simple, hopefully pretty straightforward. Aluminum sulfate then is a lot like it. We need to do the same procedure, and this time we do need to account for a little more stoichiometry. So the molecular weight for aluminum sulfate, people often call it alum as a kind of trade name or a typical name. This one is 341.37 grams per mole. And we recognize that each molecule of aluminum sulfate will dissociate and give us 2 aluminum 3+ charges and 3 ions rather, and 3 sulfate ions. Each have a 2-. So our ionic strength equation then is a little more interesting here. We said there's no sodium chloride, we just have the alum, so we'll take the aluminum times essentially 9 plus the sulfate times negative 2 squared. And that's going to be our equation for it. And then, of course, we have to solve for each of the concentrations. So just like we did last time, I'm going to skip just a tiny bit of it and say that there's some amount of alum that we added. I'm just going to say the concentration added. Well, I'll be consistent. We'll write it out. We'll say Al2SO4 and remember, this is not existing as a concentration in solution. I'm just saying that that's the moles of it that we added per liter in the water. If we do the calculation, we should get 0.0183 moles per liter. That means we take that number and we can multiply it by 2 to get our aluminum concentration and multiply it by 3 to get our sulfate. So aluminum then should be 0.0366 moles per liter, and our sulfate would be 0.0549 moles per liter. Okay, didn't really give myself room here, but when we put in these values, we should get an ionic strength of 0.275. We'll do the box for each of these. Okay. Any questions or issues with that? Okay, good. And by the way, if you are like me and occasionally slightly less organized with your work than you meant to be on your homeworks or exams, please do me a favor and draw attention to your final answer. That'll cost you a very, very small amount of time, might even save you some time when you flip back through to check it or something, and it'll save me a lot of time and headache. And you always want me to be happy when I'm grading your papers, not frustrated that I can't find your answer, you know? So it's always a good idea. Okay. All right. The next part, part C, says, given that ionic strength that we just found in part B, what is the resulting activity of sulfate in those conditions if we use the Davies equation? And let's assume 25 Celsius, and the table at the back of the assignment was what we were pointed to for the parameters. And if you go back and look at it, I don't have it on the slide here, but this was table, I copied it from a book. It was 2-1, and it listed a bunch of values for A. That's what we really needed to look at, is at 25 degrees Celsius. The A was equal to, do this. A was 0.5085. That'll make more sense if I start where maybe I should and say the Davies equation is what we use to pull in the ionic strength and find an activity coefficient. Right, so activity for sulfate is going to be equal to the activity coefficient for sulfate times the concentration of sulfate. Right, that's the definition of activity. And another way we could write that would be curly brackets for sulfate. That would be fine too. Okay. At any rate, this gamma here, the Davies equation is something we have to get that value, and that is in the form of log of gamma is equal to negative A times the charge of sulfate, in this case, squared, times the square root of I divided by 1 plus the square root of I plus, and one of the equations says B, but Davies is what assumes that this is, goes ahead and assumes this is 0.3. 0.3 times I. Okay, so if you were to look in the book, there's another version of this that has some units here or some things that you could look up, but essentially it says typically we can, if we take a look at the typical units we put in there, oftentimes that comes to 1. So that's the form I used. If you went through and used the little B and the A naught that go in there, I will notice that when I'm grading, and it will probably be a very similar answer to what I have. And I wouldn't really fault you for that. I think the Davies equation typically assumes that's 1. Okay, at any rate, this A is what we're talking about here. Z should be -2 because sulfate has a -2 charge, and we just put in the numbers at that point, right? So then we get log of our activity coefficient, bless you, should be equal to -0.617. And then we can take 10 to the power of both sides to get rid of the log and get our activity coefficient to be 0.242. Now that means our activity itself, which is what we were solving for, should be 0.0133 moles per liter. And one thing we can check here, we see that activity coefficient, that's 0.2 something, maybe near 0.25, so it's a quarter of the sulfate that we actually have is acting like it's sulfate. And then we could flip back and say, okay, well, if we take this 0.013 number, our real concentration should be something like 4 times that. So if we go back up and figure out, okay, we solved for sulfate, that was 0.05 something, and this is 0.01 something, yeah, it's about 4 times or so, just in the ballpark. That makes sense. And we can also remember or check that our activity coefficient should pretty much always be between 0 and 1. Or at least in normal cases. There are some exceptions, so I'm just going to say usually. And usually we'd expect if we're adding some ionic strength and causing things to interfere with each other a bit, the activity is going to drop a bit. But it doesn't really make sense to have a negative activity, and I think it would take some pretty special circumstances to have hyperactivity, so above 1. Okay, any questions, issues on that? All right. Okay, number 2, we have a geochemically important reaction, which is calcium carbonate. I didn't specify it, but the most common form is calcite, and when you go and look this up, there's probably more than one type of, I think argonite or something was another type. If you use some other values for a different mineral, you're going to be very close to the same numbers, and again, I'll probably be able to notice that, and it's no problem. Turns out some of the books, if you were to happen to use an old reference book for the thermodynamic coefficients that we have to look up here, some of them are a bit older and, might have calculations may have changed a little bit also. So I'm not going to be too particular, but it'll become pretty obvious if you're close or not, right, as we go through this. Okay, there was one trick to this question that I didn't mean to leave in here, but I did take this from a book at some point, and they left a little trick in it. And that is that we are given this reaction, but if you don't look closely, you didn't recognize that it's not balanced, the equation itself. So how many of you balanced that equation? Anybody? Okay, You're not alone. Last semester, I did this problem as I was teaching the grad class, and I didn't recognize it at first. And then this time, as I was going back and preparing it again, I also forgot again. So you're in good company, but if we take a look, what do we have to change? Like, balance that in your mind for a moment. Yeah, and what about it? We gotta have two of them. Yeah, exactly. Okay. So I hope I see a lot of wrong answers on this one. All the same exact wrong answer as if we didn't balance that. That's my hope, since none of you admitted to not balancing the equation. Okay, but this is good. I'm not going to take a lot off for that. So once we have this equation, and on an exam, I'm going to be a little more careful to say, balance this equation, part A, if I decide that's important. So I'll do my best to not introduce accidental tricks. Sometimes it happens, but I'll try to be fair if I accidentally trick you. At any rate, once we have that in place, and this is good so that we can see how to account for that, the overall process should be relatively straightforward. The best thing probably to do is to write out all of the Gibbs free energies and enthalpies that we need. So let me back up one step and say, what is the question asking? Well, calculate the standard free energy for change, so Gibbs free energy, and the enthalpy for this reaction at 25 Celsius in 1 atmosphere. So we're at standard conditions, and we want to know the delta for the reaction, delta G naught, and delta H naught. Which means we need to know the delta G standard for the products minus the reactants. Likewise, we can do the same thing for the enthalpies, because this is the change that happens upon reaction. Okay, so for each of these then, we need to go and look up, okay, what is the Gibbs free energy of formation for calcium carbonate, and for CO2 gas, and for liquid water, and for calcium, and for bicarbonate. So for each of these, we need to go and look it up. So what I did was I went ahead and just made a table, and I said, let's get all the delta G's here and all the delta H's here, and each of these are in kilojoules per mole units. And here's where, if you used a different lookup table, it could certainly be a little different. Let's go ahead and do this. And I went ahead and said, let's get it for calcite, for CO2, for H2O, calcium, and bicarbonate. Okay, so do you guys want me to write up all this? I don't think it matters too much, right? I could put in all these, but for the moment, I'll trust that you can look those up. It's certainly possible to make a mistake there in looking them up and moving them around, but it's not anything more complicated than looking it up in an appendix, right? Just making sure you match the right ones. And just to note that I happen to use calcite for this one. Okay. So given that, another thing we could do is we could add a column to say, okay, what is the stoichiometric coefficient here? And then as we are doing the products minus the reactants, multiply that into. So when we solve these, we would say the delta G for products would be the delta G, so 1 times calcium plus 2 times the bicarbonate, and then minus all the reactants. All of these are negative numbers, so it's kind of like, subtracting a negative is kind of like adding. But you would get the picture, and if you put all those in, including the 2 coefficient there, importantly, delta G for the reaction should be 33.21 kilojoules per mole. Now, I think it was a much larger number, something like 600 something, if you didn't include the 2. So it makes a big difference. But the good thing is, if you're nodding your head like, yeah, that looks familiar, you're pretty much doing it right, just missing the trick, right? Okay, so then the delta H for the reaction, I think also was like 650 or something, but in this case it becomes negative 40.1 kilojoules per mole if we get the stoichiometry right. Okay. Does that make sense? Aside from the trick? All right. All right. So next up, we want to calculate the equilibrium constant. And of course, this is going to look a lot different if you have a different delta G here. We can use the equation, and this is a good example of the type of equation I'm going to give you. We have the natural log of the equilibrium constant is negative delta G for the reaction divided by RT. Of course, we can also convert this to a log. So log of KEQ, and then we add that 0.203 factor at the bottom, 0.2303 or something. But for the moment, I'm just going to put it as natural log. And if we solve this, we can say, well, I know delta G for the reaction. We just found that. It's 33.2. And R here is the ideal gas constant. Typically, I'm going to use the 0.08821, I think. This is liters per atmosphere, liters atmospheres per mole Kelvin. Because we're working with moles, we're typically assuming 1 atmosphere, or dealing with pressure in atmospheres, dealing in kelvins, and it's like moles and liters. Yeah.
So I use the other gas constant in terms of joules, since it gives free energy with kilojoules.
Yeah, you know what? That actually might be the better way to do it. I was looking at some notes and it had some funny units in cubic meters, and I was like, well, I'm not going to do that. Theoretically, you probably need to, don't you? So what is that one? Let's do that one instead.
8.314 joule per mole Kelvin.
Joule.
Converting that to kilojoule, 8.314 times 10 to the minus 3.
Yeah, I think that I should have actually been using that one. So that would be 0.008314 kilojoule per mole Kelvin, right? Okay. This is good because I was looking through my notes from last time. I was like, why did I get that number? I'm getting a different number, but okay. So we're going to use that one. Don't use this one because we do need to get the units to cancel. And if this is kilojoules per mole, and down here we need also then kilojoules per mole in total. So if we have kilojoules per mole Kelvin times temperature in kelvins, that all cancels properly. So this was my mistake, which is making more sense now. So thank you for that. Okay, and on the exam, I'm going to give you a lookup table that will have a few values for R. Occasionally, we might need this one, and I don't know what I was thinking this morning. That's not right now. So always watch the units. Okay, so then with that, we can take the natural log, or so we can say the natural log of KQ is going to be equal to that. And if somebody could do that, we can take the 33.21, so negative 33.21, divide it by 0.008314, multiplied by our temperature is going to be 298.15. That's our 25 Celsius converted to kelvins. Anybody have that number for me?
Yeah, ever since the unbalanced equation, like, my numbers are pretty bad.
Okay. Well, if you're too slow, guys, then I'll do it. Okay, so negative 13 point, let's say 0.40, negative 13.40. Okay, so that's our natural log of KEQ. So we can raise e to the power of both sides to get our KEQ. And it'll look a little better, the number will look a little better once we do that. Hello? Okay. So you can do in Excel, EXP is the function to say e to the power of something, and then put in that number. So e to that, our KEQ then is 1.52 times 10 to the minus 6. Okay. The process, at least, does that make sense getting there? All right. So the last part says, will an increase in temperature favor a shift towards products or towards reactants? So really what this is asking is, what's happening to the K if we change the temperature? And specifically if we increase the temperature. Now, intuitively, we probably all have the impression that if we heat something up, that tends to promote some more reactivity of some sort. But that's a little bit, that's kind of faulty of an assumption, right? So especially with something like, it's especially our sense if we're trying to dissolve something, right? Because we think, oh, if I'm making sweet tea or something, the sugar will dissolve a lot faster if I heat it up, right? We feel like this is going to, no matter what, if we increase the temperature, we'll probably get more products because that's the dissolved phase, right? That's what it feels like, but that's not necessarily true, at least not for every type of thing happening. And it comes back to the thermodynamics. So what we ought to do is take a look at it from the thermodynamic equations. And if we take a look back at kind of how some of these pieces were derived from, at some point we got this equation where the change in natural log of KEQ per change in temperature, we could relate to the change in enthalpy for the reaction. Now, we integrated this, or rather let the book integrate it, and said this is going to be the natural log of K at temperature 2 minus the natural log of K at temperature 1 is equal to this delta H for the reaction divided by RT, all that times 1 over T1 minus 1 over T2. And we said this is the Van 't Hoff equation, right? So we can use that to see what's happening to the K when we change the temperature. So what I did was I wanted to compare K1 to K2 in some way and just test some random temperature too. That's kind of how I went about it. So I said, let's just say T2 is 300. I think I said 320 actually. Now that's pretty arbitrary. Big enough difference to see a difference, but it could be 500, could be 1,000. You could even go the opposite way and say, well, what happens if it goes down to 200? You know, how does that change it? And we expect the backwards of that change probably. So anyway, you could play around with that, but the important part is what are you doing to compare the Ks? And one thing you can do is recognize that the natural log of something minus the natural log of something else is the same thing as writing the natural log of that first something divided by the second. Okay, so this gives us a spot where we can get a ratio of one of the Ks to the other. And that means if we solve it and we put, let's take for a second the scenario where we put in exactly the same temperature. So T1 is equal to T2. What happens? Well, this on the right side becomes 1 minus 1. So there's a big fat 0 there. That means on the left side of the equation, we're taking the natural log of 0. Or excuse me, the natural log of this something equals 0 means the thing inside the brackets is 1. The ratio is 1. They're the same. So if I then change T2 one way or the other, I can find some number. And just as an example, I did that when T2 is 320, this ratio, and then I took I didn't solve that exactly, or I didn't write that down, but then I just said K at temperature 2 divided by K temperature 1, that was equal to 0.89. So I just didn't write that down, but you could certainly do that, or I can bring up the Excel if you want it. When I did that, I recognized at this temperature, or excuse me, with K, the second temperature, that K is a smaller K, right? If this number was greater than 1, it would be a bigger K. If it was smaller than 1, it's a smaller K. So the K decreased. Now, what does K correspond to? Remember, K we set equal to the products over the reactants. And the question is asking us, are we shifting towards products or shifting towards reactants? So if we make the K larger, more products exist and fewer reactants. If we shrink the K, more reactants exist and fewer products when we find the equilibrium, right? So K is the thing that's telling us where that balance arrives. So if we just decrease to the K, so K2 is smaller, therefore more reactants. Yeah.
So I kind of came to the same conclusion, but I pretty much just applied the Chatelier's principle such that, like, so this is an endothermic process. The enthalpy is negative.
Yep.
I mean exothermic, right? So the enthalpy is negative, and so you can essentially like look at the heat like a product, right? And if you add excess products, it'll shift to reactants. And so I didn't do it like a mathematical way, but
yeah,
would that be?
I think that's I think basically you're dealing with it at this level here, and that's fine with me. If it reliably gets you the right result, which it sounds like it will, because it's essentially tying things together, I don't see a problem with that. Okay. All right. Any other questions? All right. Oops. Did I skip? I did. I hit the end button, not the next button. Okay. So next up, we want to answer a few questions about dissolving some acids. And this is kind of tying in or bringing up some of the different fundamental equations that we might use. So for both of these, we want to get 4 equations that we would need to solve for a pH of a system. Not to say that we are doing it necessarily, but I'm having us consider what might be needed. So we're looking for the mass balance, the mass action, electroneutrality, and we'll also consider the proton balance in case that might be appropriate. Okay, so for this one, we have 0.001 moles of HOCl added to 1 liter of water. So we've got a little bit of hypochlorous acid. This is bleach. And ultimately, we want to find something that could get us pH, right? So we need to find H plus somehow. So we're not going to even set up all of the equations to the point where we are solving for it, but I want us to think about how we might get there and how these equations might be coming together. So first up, we might start with mass balance equations. And we can take a look to see how many independent ones we can find. The first would be the total concentration of HOCl was given to us, right? So we have some C total, that was 0.001 moles per liter. The other thing we could say about the total concentration is that should be comprised of HOCl and any other component it might dissociate to, right? So we need to recall, or perhaps this is something that I hope that you would know, is that HOCl should be in equilibrium with OCl minus and H plus. And I hope you'd know that because we've talked about it a few times by now. This is free chlorine, and this is something, since we've talked about it a lot, hope you know that. Okay, so to recognize that, then we would see the CT would be comprised, so the total amount of moles of chlorine would be in those two forms, right? And we can pause and think about it and realize, okay, these are 2 different equations. We can relate them together, but they are independent equations. And so that would be 2 that we need. We can take a look at, of course, mass action equations, right? So I don't know, we'll maybe just call them just the equilibrium. That's pretty obvious, and we know this should be an independent one. The equilibrium for this, if we're given some constant, or even if we don't know the constant yet, we still have the equation that this should be the products over the reactants, right? And here's the first time we're seeing H plus show up. Okay. And by the way, we're not not really going to go there at the moment, but the for the mass balance, we could rearrange them in terms of the alpha fractions, right? Alpha being the portion of this one of the total. We can manipulate those and rearrange those into alpha fractions, which is one way to relate them to this mass action equation. Okay. Next up, I think it makes sense to look at electroneutrality equation. the electroneutrality equation. So we're going to put all of the cations on the left. I'm just going to go ahead and start with H plus and OH minus on the left and the right, and then just add from there. So any other cations? Nope. Other anions, we have OCl minus. Okay. So that gives us 4. Yeah.
Should it be HOCl in the denominator of the equilibrium equation?
Absolutely. Thank you. Okay. So then we've got this electroneutrality equation, and we could think about and go ahead and write up a proton balance equation. You know, we didn't really talk enough about it to say for you to determine at this step, are we at one of those equivalent points? Does it even make sense? But just in case, let's take a quick look and see if it is maybe useful. Okay, so I'm just going to put a question mark here. We already have 4, so it's not like we really need it. But the proton balance equation would look like this. Always start with H plus on the left and OH minus on the right, because each of those, given water, lead to the formation of the other. So then anything else we add that leads to the formation of an OH minus, I don't think anything, you know, we've added HOCl, so we have OCl minus as the only other species that can be here. So the formation of OCl minus did not lead to the genesis of OH minus, but it did lead to the genesis of an H plus in solution. So we actually put that on the right side. And there's really nothing else to add, but we see that this is redundant with the electroneutrality equation. And if we take a look back when we did the simple case of HA, some generic acid, that's exactly what was going on, right? In some cases, like this one, pure water plus HA, these two became redundant, and it was kind of pointless. Okay, so even though we don't even know if we should be using proton balance at this point, doesn't even matter, it was redundant, it's not giving us anything new. But we already had 4, we already answered the problem, we're good. Okay. So probably we could find the pH with those 4 equations of that solution. Okay. All right, we're good on that. Do the next one. This time we have NaOCl, and we're basically going to go through the same process. We have a little difference here because we have added sodium instead of the HOCl. And this could lead to it being slightly basic instead of the other way. So we still need to recognize the overall equilibrium involved, HOCl in equilibrium with OCl minus and H plus. And also that when we added NaOCl, this should all dissociate so that sodium can become a little spectator ion, and we have OCl minus, which then is in equilibrium with HOCl. Okay, so let's do the same thing. We've got some mass balance equations and a mass action or equilibrium, same as last time. And we'll go ahead and start by saying the total concentration is a bit higher this time, 10 times higher, 0.01 moles per liter. And we can actually add another piece here to say that this is also equal to the total sodium concentration. So I'm not sure if this counts as 1 or 2 different equations, but I'm just going to put that up there as one of them. There's no other source of sodium, so for every amount of chlorine that we add, we're adding 1. For every molecule of chlorine in any form, we've added 1 ion of sodium. Yeah.
fully dissociates, right? Because
Yeah.
okay.
Yeah, anytime we're dealing with some typical acid or something like that where we have, let's say, just a chloride or just a sodium or maybe potassium or something like that, unless we're told otherwise, simple ions like that tend to just completely dissociate and then they act as spectators. Okay. I would have to tell you specifically that there's a sodium that precipitates into some solid, right? And we have some equilibrium to deal with there. Thankfully, a lot of times in our typical chemistry context, the monovalent ions typically just hang out and watch. Sometimes with calcium, that type of thing will become important where we might have some dissolved and some as a solid, and we'll have to worry more about that. Okay, so that would be one of them. Another, as we did last time, we could also say all of the chlorine concentration will be summed by the OCl minus and the HOCl. And of course, we have the same equilibrium constant equal to H plus times OCl minus divided by HOCl. And I got it right this time. Okay, so then we can look at the electroneutrality equation. We'll start with H plus on the left and OH minus on the right. This time we have sodium also as a cation. And we still have OCl minus. Okay, so that would give us four equations there. Again, let's take a look at the proton balance equation. And until we really get into that and talk about buffering and some of the titrations and stuff, I'm just going to tell you right now, we're not going to use it, but I would like for you to be able to create a proton balance equation. Okay, so if you used that as one of the equations here, I'm fine with that. Maybe you took my approach and took the ones that were a little more known and sure about. But for the exam, I might have you write a proton balance equation, but I'm not going to ask you anything about whether or not you're supposed to use it yet. Okay? Maybe I'll have you do some manipulations with combining some of these equations, something like that, but not the titration stuff. Okay, if we were to check proton balance, then at least to see if we get a fifth equation here, well, again, we look at which species led to the formation of an H plus or an OH minus. H plus will always lead to the release of an OH minus into solution. So we'll have that on the left, and OH minus leads to the formation of an H plus. And in this case, we really don't have anything that's causing the generation of an OH minus, H plus. So we don't have anything else on the right. On the left, however, we could say that the formation of HOCl is basically taking a proton out of solution, which is the same thing as releasing an OH minus into solution. So by thinking of it that way, we could add HOCl here. And that does appear to be a fifth equation, again, if we are able to use it at an equivalent point.
So we're putting HOCl on the left because when it reacts with water, it gives off hydrogen to water.
it takes a hydrogen away, but if you imagine it taking a hydrogen away from a water molecule, so let's say H2O plus HOCl. Not HOCl, sorry. The formation of HOCl required what from water, right? So we have to think about OCl minus reacting with H2O. What did it have to do? It had to strip away one hydrogen, right?
Oh, so the base had to pull
So
out.
then we're left with an HO minus, right? So by stripping away one proton from water, we've generated an OH minus. That's the formal way to think about it. So the formation of HOCl by OCl minus's reaction in water released an OH minus. I think it's also fine to think about it in terms of it has taken away a proton from water, and so it's going to show up on the left side. If you think about it, on the left side we have anything that takes away protons from water, and on the right side it's anything that takes away that adds protons to water. The formation of it does so. Good enough? Okay. All right. So next up is a problem that kind of is just hinting at, again, not the full scale of solving the carbonic acid system, but kind of just showing ourselves what's coming, and in the short term, how do we simplify it too much, too overly simplified, as I say in the problem, so that we can look at what we would need to handle it with these different equations, but not really go there just yet. Okay, so rainwater is typically a bit acidic given this reaction. So we're going to imagine we have a closed system with just a little bit of dissolved CO2 in it and pure water. And the first part, we're going to assume that the carbonic acid that is formed completely dissociates by the following reaction, and it all ends up, every molecule of it leads to 2 protons, right? So we form H2CO3, and then every one of those releases 2 protons. And I say, specifically, this is not realistic, right? We know there's equilibriums involved, but we're going to ignore all that right now, okay? So the point is just to solve this as if it was a strong acid and it's going to release all of that acidity. So what we need is to know, well, how many moles per liter did we add here? So we'll get the molecular weight of CO2 because that is what we added. That should be 44 grams per mole. We added 25 milligrams. I'm going to write that as 0.25 grams. So divide 25 by 1,000 of CO2. And I'm going to go ahead and multiply that by 1 over 44 grams per mole. Or I guess I could say 1 mole per 44 grams. And divide all of that by the 10 liters that we have. That'll go ahead and give us our molar concentration of CO2 that we dissolved. Turns out that is 5.68 times 10 to the negative 5th moles per liter. Okay, so once we have that, we know that we have a 1-to-1 CO2 to carbonic acid relationship. So that means we have 5.68 times 10 to the minus 5 moles per liter of carbonic acid. And we can say that the H plus will be 2 times that. H2CO3. And again, since this is all dissociating in our weird problem here, I'm going to say that is added like that. So I'm just adding that little note for myself to know that that's all going that way. Okay, and really that's going to be the strongest influence on H plus. And we weren't told anything else about what's in here. So we're going to basically say that's the amount of H plus we have in solution. When we solve that, that becomes 1.14 times 10 to the minus 4 moles per liter. So pH is the negative log of H. So if we convert that to a pH negative log, that becomes 3.94 as our answer. Okay.
And I guess the main assumption is that just under these like arbitrary conditions that it's like associated completely that by the 1-to-1 ratio it's always going to be like equal to the H plus.
Yeah. So when we have an addition of a strong acid like that, and we assume, I mean, clearly this is not actually a strong acid, but we assumed basically that it is. That's in this case is the 1-to-2 addition, but we're really assuming there's no other realistic sources of H plus. Now, water itself dissociates a little bit, but that's that equilibrium is pushed based on the current pH, right? So it's kind of suspect or susceptible to the addition of this that's pushing a lot more H plus into solution, if that makes sense. Did that answer your question? Okay. Okay. Part B then says, in reality, we have two equilibriums at play, and we're just going to take a look at the acidic side here. So the Ka for the following reaction is 10 to the minus 6.35. That is a reaction between carbonic acid and bicarbonate with H plus. So the question says, what would the ratio of carbonic acid to HCO3 minus be if the pH of the solution was 5? We're going to assume there's no other important reactions at play, keeping things pretty simple, just looking at that one reaction and what do we see from it here. Okay, so we need to take a look at what is our equilibrium equation here, and we're just going to go ahead and say that's K. We could maybe call it K1 if K0, well, I guess maybe K0 would be fine too. I'm just going to call it Ka for now. So Ka here, that's the 10 to the negative 6.35, and we know that's going to be equal to the products over the reactants for this equilibrium, right? So the H plus times HCO3 minus divided by H2CO3. And what we're looking for is the ratio of H2CO3 to HCO3 minus. So what we want, the ratio will simply be H2CO3 over HCO3 minus. So we just need an equation that gives us that answer, right? So we can then take a look at our equilibrium, this mass action equation, and see, can we rearrange that? Can we find this ratio just from there? Well, that's all we really need to do. So we already almost have the ratio here, we just have to flip it. So what we're going to do then is just a bit of algebra, take H2CO3 multiply that on both sides, and I'm going to go ahead and divide both sides by 10 to the negative 6.35. And of course, we can then divide both sides by the bicarbonate. And what we'll find is this is going to be H plus divided by the Ka is the ratio that we need. And when we divide one by the other, So 10 to the negative fifth is our pH, divided by 10 to the negative 6.35. We can even just look at that, right? That's going to give us an answer that is, you know, if we do the little logarithm or exponent math here, so 10 to the negative 5 divided by 10 to the negative 6.35. I mean, we could put this in a calculator, but we also recognize, if we stop and think about it, this simplifies to 10 to the 1.35, right? It should. So that means it's going to be between 10 and 100, right? 10 to the 2 is 100. 10 to the 1 is 10, right? So it should be, I don't know, 2 to 3 times 10. So we do that answer and we find it's 22, I think, right? 22.39. So there's 22.3 times, 39 times as much H2CO3, excuse me, carbonic acid as there is bicarbonate at pH 5. That would be the way to say it. Okay. That makes sense? Good on that? All right. That brings us to the last question, which you had the most questions about. This says benzoic acid, which we don't really know too much about. It has a pKa of 4.2. So that means the Ka is 10 to the minus 4.2. Can be used to inhibit biological growth. The following data showed the dependence of the minimum required toxic concentration on the pH of the solution. So we've got data by pH, and it's showing the minimum benzoic acid concentration required. What I'm going to say here is that, let me finish the question. Interpret the concentration required for growth inhibition in terms of the acid-base chemistry of benzoic acid. Which is the effective species, benzoic acid or benzoate anion? So we could go to Wiki and look up what is benzoic acid if we want to, or just by that, we know there are 2 species. One I'm going to call BZ with an H, the acid, or one BZ with a minus, which is an anion, right? There's some anionic form of it. And what do we know about a pKa? Well, products over reactants, right? So we should have something that looks like this if we were to write it all out. And that, you know, also we should have some understanding that this is going to be some equilibrium. Right? All this to say is that if we increase the pH, we're going to end up having the version of this that has fewer protons. If we decrease the pH, when there's more protons in solution, we're going to have the version that has the proton on it. Right? That's kind of the deal here. And the midpoint is going to be at the pKa. So we can draw a midpoint somewhere between 4 and 4.5 and say, okay, if this is where we have 50-50 of HBZ and BZ minus, well, down here we have more BZ minus, and up here we have more HBZ. Okay? All of that so far is probably what you can recognize from class, right? I hope. Or at least we're building that way. So the challenge here is to understand how to apply this pKa to sort this data in some way. And now we look at it and to say, what is the data actually telling us? Minimum concentration required. So this required a low amount. And this clearly requires a high amount. So if it requires a small amount of concentration to inhibit growth, that means it's more toxic. So smaller amount, more toxic. And so that's how we answer the question, to say, okay, given this data, the benzoic acid would be the more effective species or more toxic. Okay. Does that make more sense now? A little simpler than you thought? How many of you went to like wiki and what is this benzoic acid thing or wherever?
Well, I guess I tried to do it quantitatively. Like I just used one of the data values and like plugged in, and then I made a ratio of the benzoate anion to the benzoic acid, like based on the same convention from the last question. I ended up getting like 1.995 to 1, but I just didn't really
know what to do with it from there.
Yeah.
But you can kind of see, like even with that, you're kind of able to see the different pieces coming together to tell you something about the system, right? Even though this might be more of a biological or microbiological system or something, this is the chemistry side of it that we're looking at. Yeah.
Yeah, back on the microbiology part of it, I just kind of thought of charged particle as a hard time diffusing across permeable membranes, so the neutral one is probably going to be the most effective.
That could be exactly why. Yeah, it's a very good point. So if you know anything about kind of the membrane integrity of a cell, they often control what's coming across them based on controlling the charge at that surface. And if you have a negatively charged ion, even if it is quite toxic, if it can't get in the cell, it's not going to exert that toxicity, right? It's a very, very good point. Okay. Unless there are any other questions, comments, see you on Tuesday for the exam. All right, have a good weekend.